In this unit, we will see an application of the determinants to the resolution of linear equation systems, using what is known as the Cramer's rule. We will see, first of all, how we express a linear equation system, and then we will see how to apply the Cramer's rule to solve it. To do this, we must remember what is a linear equation system and what is a determinant of square matrices and how they are calculated. So, we will start by remembering that a linear equation system is a set of linear equations such as the one you have on the screen, and that solving the system is to find all its solutions or to conclude that the system does not have a solution. On the other hand, the determinant of a square matrix is a number associated with the matrix that we denote by this expression that you see on the screen, and which will help us to, for example, know if the matrix is invertible or not, depending on the value of the determinant. If the determinant is 0, then the matrix is not invertible. And if the determinant is different from 0, then the matrix has an inverse matrix. Well, after remembering this, we return to linear equation systems, and we have that a system of m linear equations with n unknowns. x1, x2, xn has this shape. First equation, second equation, m equation, unknown x1, x2, xn. The a sub 1, 1, a sub 2, 1, a sub 2, 2 are the coefficients of the system, and the b1, b2, bm are the independent terms. Well, this system also admits an expression as a matrix product, where I would put the matrix in which I only put the coefficients of the unknowns multiplied by the vector of unknowns equal to the vector of independent terms. As you can see, the product of this matrix by this one, a1 on 11 by x1 plus a12 by x2 plus a1n by xn equals b1 would give me the first equation. Second row times this vector equals b2 would give me the second equation, and so on. Well, we can write this more briefly as a times x equals to b, where a is the matrix that is framed in blue, the coefficient matrix, x is the vector of unknowns, the one that is framed in red, and b, the one that is framed in green, is the column vector of independent terms. Well, here we see that all systems can be written matrixly, whether it is a system with the same number of equations as in cognates or not. For example, this system, 2x plus 3x minus 4z equals to 2, x minus z equals to 1, and x plus 2x plus z equals to 0. Well, we would have a matrix with these coefficients, 2, 3 minus 4, 1 minus 1 minus 1, 1, 2, 1, obviously without exchanging coefficients between equations, and without exchanging the order of the variables, variable x, variable y, variable z, vector of unknowns x and z, and independent terms 2, 1, 0. Well, this matrix product equalized to this vector of independent terms results exactly in this system of equations. And as I said, this has the same number of equations as unknowns. But although it does not have it, it also admits a matrix expression. For example, here I have 2 equations only and 4 unknowns, x, y, z, and t. Well, I would write the same coefficients, 1 minus 3, 2 minus 1, 1 minus 3, 0, since here the z does not appear, minus 1 times x, y, z, t equals to 4, 1 independent terms. Whatever it is the size of the system, it can be expressed matrixly, regardless of whether it coincides with the unknown number of equations or not. Well, since this is seen, let's see what the Cramer's rule is. The Cramer's rule is a way to solve systems of linear equations in which the unknown number coincides with the equation number, m equals to n. In that case, the matrix expression would be, as we have said, this one here, or approximately, a times x equals to b. And if in addition the matrix A is invertible, what happens? Well, I can multiply by A, inverse on the left, on this side of here, so that it would have that times x equals to b. It is the same as A, inverse times x equals to A, inverse times b. That is, if I multiply a side of the equality so that the equality remains, I have to multiply also the other side of the equality. And on the same side, let's remember that the matrix product is not commutative. Therefore, it would have A, inverse times a times x equals to A, inverse times b. A, inverse, times A is a matrix, and it's inverse. This gives me the matrix identity. And the matrix identity times any matrix is the matrix itself, then x. All this part is reduced to x. And on the other side, I have A inverse times b. Then the system is solved. X is equal to A inverse times b. Therefore, we have that the system is determined and consistent. Of course, this always happens when the A is invertible. And to be invertible, it has to be a squared matrix. Then, In that case, we can apply this rule, which is known as the Cramer's rule, and which says that x is equal to A inverse times B. Let's remember x is x1, x2, xn. The A inverse, if we apply, for example, the method of the adjoints, we could apply any other method. But if we applied the method of the adjoints, it would be 1 divided by the determinant of A times a matrix where each element is the adjoint of the corresponding element. Here would be the adjoint of element 1, 1. Here the adjoint of element 2, 1. Not the adjoint of element 1, 2, but 2, 1, and so on. Times the matrix B, which is the matrix of independent terms. Well, this is the Cramer's rule. Of course, in practical effects, we are interested in knowing who is x1, x2, xn, trying not to have to calculate all these adjoints, especially if the size of the matrix is very large. Well, by doing these operations, theoretically, what is truly known as the Cramer's rule arrives, and it is that each of the unknowns can be calculated as the division of 2 determinants, a determinant in the numerator and the determinant of A in the denominator. How? Well, the following way. We know x1. Well, in the denominator, I will always have the determinant of the matrix, A. And in the numerator, instead of having to calculate all these determinants and then this product of matrices, what I will do is calculate a determinant, where I will put the determinant of the matrix A, where I will have changed the column 1 for the independent terms. That is, A sub 1, 1 is replaced by B1. A sub 2, 1 is replaced by B2. A sub 3, 1 is replaced by B3, and so on, to A sub n1, which will be replaced by Bn. That is, I replace the column 1 because it is the variable 1 by the vector of independent terms. This determinant divided by this other determinant gives me the value of x1. How will I obtain x2? Well, in an analog way, the determinant of A in the denominator and in the numerator, I will have the determinant of A, where I have replaced the column 2, since it is the variable 2, by the vector of independent terms. And so on, x3, the determinant of A in the denominator and in the numerator, I will replace the column 3 by the vector of independent terms, etc., until I reach the last one. Xn will be the determinant of A in the denominator. And in the numerator, I will replace the last column, the column n, by the vector of independent terms. Calculating these determinants, making the coefficient with the determinant of A, which I will have calculated initially to know that the matrix is invertible, well, I will already have the value of the unknowns, x1, x2, xn. That is the solution of the equation system. Let's look at it with an example. Imagine that we want to solve this system that you have here. The first thing we do is to build its matrix expression. In the matrix form, I have a matrix of coefficients, 2, 3, minus 4. 1, minus 1, minus 1, and then 1, 2, 1, the vector of unknowns, and the vector of independent terms, 2, 1, 0. Next, we calculate for this coefficient matrix A, if it is invertible or not. As the determinant of O, A, in this case it is minus 16, applying the rule of Sarus here, different from 0, we can make sure that the matrix has an inverse, and therefore we can apply the Cramer's rule, because we know that the system will be compatible and determined. And what's going to be the solution? Well, let's see that it is x, that it is y, and that it is z. What is the x? Well, the x, as it is the first of the unknowns, will be 1 divided by the determinant of A. Remember that it was minus 16 multiplied by a determinant, which is the result of taking the matrix and changing the first column by the vector of independent terms. Then, instead of 2, 1, 1, I'm going to put 2, 1, 0. I calculate this determinant by the rule of Sarus. I know that it is minus 9, then minus 9 divided by minus 16, it is 9 divided by 16. Let's go with the y. The y is the second variable, with which I'm going to have to replace the second column. I'm going to have to eliminate it and put the 2, 1, 0. I calculate this determinant and I get 2 minus 2 divided by 16. That is what the y value is. And the last, the z, is the same. I take the last column and replace it with the 2, 1, 0, which is the vector of independent terms. I remove this one here. This determinant, because of the rule of Sarus, is worth 5. Then the z is worth minus 5 divided by 16. Since we have reached that the system is compatible and determinanted, and its solutions x equal to 9 divided by 16, y equal to minus 2 divided by 16, and z equal to minus 5 divided by 16, we have found the solution of the system by calculating determinants. Well, as you can see, we have seen that the whole linear equation system has a matrix expression, and that if a series of conditions is met, we can apply the Cramer's rule to solve it.